Okay, this is lesson 1.2, uniform acceleration. This is basically about kinematic equations, how you can solve for values, as well as motion due to gravity, a specific example of uniform acceleration. So let's get started. There are 5 main quantities of motion that we need to talk about. Time interval, not just time, but time interval. Displacement, not just position, but displacement. And then for some reason, initial velocity and final velocity, not change in velocity. And then acceleration as well. So those are the 5. And coincidentally or not, there are also 5 kinematic equations. And the funny thing is, each one forgets one of these variables. They just don't use one of these variables. And that's very nice when it comes to solving problems. If you know 3 of the variables, let's say you know these 3 and you want to solve for acceleration, you can just use the equation that just does not have final velocity and you'll be good to go. You just plug it in, solve for A. So what are these equations? Let me arm you with them. First one is displacement is equal to initial velocity plus final velocity over 2 times delta t. And this looks a little bit similar to what we said in the previous lesson, where the average velocity is equal to the sum of 2 instantaneous velocities over 2 if there is constant acceleration, which there is in this case. So we can rewrite this as delta x is equal to average velocity times time, but we're just writing it in the first way because we use these 2 quantities of motion. For the second one, without displacement, it's going to be final velocity is equal to initial velocity plus acceleration times delta t. Third one, without final velocity. So this one's going to be probably the most important one you're going to encounter. Displacement is equal to initial velocity times time plus 1/2 a delta t squared. Without initial velocity, it's going to look very similar. It's like someone just changed the sign of this one. You just change the plus to a minus and replace initial velocity with final velocity. And finally, without time interval, it's going to be final velocity squared is equal to initial velocity squared plus 2a times displacement. Okay, those are the 5 you need to know, and we'll do some practice problems with them later on. But before we do that, let's just one word about kinematic equations. So if a problem says it's at rest, velocity is 0. If velocity and acceleration have the same sign, it's speeding up. So again, that works. If the problem says speeding up, that means velocity and acceleration have the same sign. And as you might imagine, slowing down means they have opposite signs. And usually, if it doesn't specify, going right and going up are positive. Okay, moving on to motion due to gravity. This is about free fall. So that's when an object falls down just due to gravitational acceleration. And you know, we love gravity. What is gravity though? So the gravitational acceleration, g, is going to be 9.8 meters per second squared on Earth. Technically, it's negative because it's going down, but you'll see where that negative comes in a second. You just plug in these acceleration values in the equations. You just replace them with this g. And so one thing you would do is, for example, the third equation, delta x is equal to vi delta t. It's going to be minus 1/2 g delta t squared. That's where the minus comes in. It is negative acceleration, but we say g is a positive value. You just have to introduce that negative in somewhere. So you just do the same thing for all those equations with a. Just replace them with g when you want to deal with gravity. All right. That's it about the content review. Now moving on to the actual problems. Starting with number 1 here, there's a baseball, leaves the pitcher's hand at a speed of 47 meters per second. So we know when you start pitching a baseball, it has to start from rest. You don't catch a moving baseball and just like pitch it forward. And so it's going to be VI equals 0. VF is equal to this 47.0 meters per second. And what is displacement? Well, that's going to be a distance of 1.50 meters. Now, knowing all this, you want to calculate the acceleration because that's what it's saying. What acceleration did he give the ball and how long did it take him to pitch it? So for now, we don't care about time, but we will in the future. And so what equation do we know that doesn't care about time? Well, that is for part A, V final squared is equal to V initial squared plus 2A delta x. So you plug in what you know. This is 0. That's nice. 47 squared is equal to 2a times 1.50. So you actually use a calculator. 47 squared over 2 times 1.5 gives you approximately 736.33 meters per second squared as your acceleration when you calculate it. So that's nice. For part B, you know all this, so you just use it along with your other values you know to solve for time. I guess the simplest equation you would do here is V final is equal to V initial plus a delta t. You know all these. Vi is 0, Vf is 47, and acceleration is the 736.33 times delta t. You just divide and you solve for delta t. That's going to be approximately 0.0638 seconds. All right, that's the first problem. We can do basically the same thing with the second problem. If you read the problem, it's very similar. It starts at rest, then moves in a straight line, has a speed of 18 meters per second, and travels 117 meters. We're given the same things. Vi equals 0, Vf equals 18, and delta x is equal to 117. We want to find acceleration, and we want to find time. Same exact things. To switch it up a little, let's find the time first. First we find time, then we find acceleration. So we can practice using the multiple equations. Then there's also another word problem extension that we don't care about right now. But what equation doesn't have acceleration? That's going to be delta x is equal to Vi plus Vf over 2 times delta t. That's going to be that very first equation we learned. And so plug it in. 117 is equal to 0 plus 18 over 2 times delta t. 0 plus 18 is just 9. So divide it by 9. 117 over 9 gives you 13. So the time interval is going to be 13 seconds. That's for part A. Pretty nice number. Not so much for part B, because now you plug in values. You can do whatever you want. I'm going to do V final is equal to V initial plus A delta t. Again, like last time, we use this equation. We know this is 0, so that's nice. V final is 18. Acceleration is what we want to know, and time is 13. So it's 18 over 13. Like I said, not a very nice number, but if you calculate, it's going to be 1.38 meters per second squared. And so that's going to be your value for acceleration. And finally, part C, it says, what distance does the traffic travel while the car is moving along the length of the ramp? So how long does it take? We said it was 13 seconds, and then times the speed of the traffic, which is 18. 13 times 18, very simple, because we know that delta x is equal to v times delta t. There's no acceleration, so this equation works. You're just rearranging the equation for average velocity, and so you just plug it in. 13 times 18, you get a displacement of 234 meters, and that's going to be your answer. All right, and last problem coming up. This one is going to be a motion due to gravity problem. Small rock is thrown vertically upwards with a speed of 18 meters per second. And so we know initial velocity is 18, positive 18 because it's going upwards, from the edge of a roof of 37 meters tall. And then it lands on the street below. So displacement is going to start on a building and then go all the way down. So it's going to actually be negative 37. It's going downwards. And we know G is 9.8 meters per second squared, and don't forget to add the negative sign. Okay, what do we want to find? What is the speed of the rock just before it hits the street? So we want V final. We do not care about time interval in this case. Well, that is for now. And so what equation doesn't have time? Well, that's going to be V final squared is equal to V initial squared plus 2A delta x. So we can rearrange that a little bit, modify it. V final squared is equal to 18 squared minus 2 times 9.8 times negative 37. And so the speed is actually going to increase in this case because double negative. So you do 18 squared minus 2 times 9.8 times negative 37. Going to get a really large number, but don't forget you have to take the square root of that. And that's going to give you V final is equal to 32.39 meters per second. So that's part A. For part B, you want to find the time. And so you have all the quantities, you just have to solve for time. So let's do V final is equal to V initial plus A delta t, always a trusted equation. And so this time we can't cancel anything, but we can subtract stuff. So we know this is 32.39 is equal to 18. Technically, this is actually negative. I'm sorry about that. This is supposed to be negative because it's going downwards. It's as it hits the ground, so it's a negative velocity. My fault. And so that's equal to 18 plus acceleration is negative 9.8, again, the negative sign, times delta t. And so you just solve for that. You move all the velocities to one side, divide by acceleration, and you're going to get delta t is equal to 5.14 seconds. That would be your answer. And so that's it for this lesson about uniform acceleration. It was a bit longer than anticipated because the content review was pretty short, but practice problems took some time. And so keep a lookout for the next video about non-uniform acceleration and derivatives and stuff like that. Yay.